Good morning, everyone, and thank you for joining us for this month's TRFA webinar. We have developed this program to help deliver education to TRFA members. The audio for today's event will broadcast through your computer speakers. Be sure they're turned on and the volume is turned up. All participants have been placed on mute. This will help us to better hear and understand the presentation. If at any time you would like to ask a question, please use the question feature located on your screen. Only the presenter and I will see your questions. At the end of the presentation, I will read any questions that were not answered during the webinar. At that time, you will be able to enter more questions into the questions feature. All participants will remain on mute. Lastly, I want to let you know that this webinar will be recorded and shared on the TRFA website for member access in the future. Today's webinar is Flame Retardants with Roger Tietze from Parts Consulting. Roger has had a long career in research and development. He holds 18 patents, and today through Part Consulting focuses mostly on application development. His expertise lies in the areas of thermosets and thermoplastics. Roger, we look forward to your presentation.
Good morning, everyone. We're going to start, and we're going to talk about flame retardants, and we're going to go into an introduction of flame retardants, and we'll talk about the types of flame retardants, the chemistry and mechanisms, which are very important. There are various applications in industry today. We will be talking about the most common test methods and the most common standards that are used today. And we're also going to talk a little bit about the economics and, very important, the health and waste disposal concerns that they're surrounding today, flame retardants, of which there is quite a bit out there today. We'll cover also some marketing and discuss the technology trends that are happening today. And finally, at the end, I'm going to give you some key takeaways to view flame retardants and their uses today. So moving on. The very first thing about flame retardancy is that we have to understand that we don't want to confuse this with flammability resistance. Flame retardant materials have been modified to decrease the effects of combustion. Basically, what they're looking for is to slow down or stop the combustion or burning process, okay? They can still burn, but they're modified. Flame-resistant materials, on the other hand, are materials that are inherently non-flammable, okay? So, talking about a fire, this is, we talk very often about a fire triangle. You'll see this in an awful lot of literature that to discuss, and very simply put, it's a triangle that has one side fuel, another side heat, and another side oxygen. These are the three elements that you need for a fire to burn and continue to burn. You remove any one of these elements and the fire becomes impossible. So, for example, there was little or no oxygen. A fire could not occur regardless of the quantities of heat and fuel that were present. Likewise, if insufficient heat is available, you can have any amount of fuel and oxygen and they won't result in a fire. What's not said in this, and what's not understood, is that there's a fourth element, and that is there has to be an ignition source. Unless the temperature gets extremely high, you need an ignition source, and very often it's another flame itself, or it's an electrical spark of some kind. So that's the fire triangle, and that is the mechanisms of fire. So let's look at the material comparisons. So we have flame resistant, and that's things like asbestos, refractories, cement, ceramic, fiberglass. These are materials that basically are inflammable. glass wool, minerals, and metals like iron, copper, and others. There are some metals that are, under the right conditions, will burn, but generally speaking, iron doesn't burn, it'll melt. Flame retardants. Okay, the most common and among the oldest of flame retardants are halogenated chemical compounds, okay, either of the chlorine or the bromine nature. There's also a large body of phosphorus-based flame retardants of all kinds, liquids, solids, etc. Nitrogen-based flame retardants today have become of particular interest because they are non-halogen, and we'll get into that later. And then there are intermittent agents, and we'll be explaining that down further. This is usually a combination of things. And there are your mineral-based additives and boron-based flame retardants also. These are the major types of flame retardants that are available in the market today. When we talk about flame retardants, generally speaking, everyone talks about two classes, okay? The first is reactive flame retardants, and the second is additive flame retardants. Reactive flame retardants basically allow you to pre-react the flame retardant into the backbone of the monomer that makes up the polymer. And so they usually form then prepolymers, and these can then be inherently already flame retardant. Additive flame retardants, on the other hand, are just simply ones that you can put into the formulation mixture at any time, and they do not chemically react. They are basically standalone ingredients inside the mix, kind of like sesame seeds inside bread. Doesn't become flour, doesn't become bread, the seed stays itself. The further subdivisions of flame retardant classifications are going to be what I just discussed: the halogen, non-halogen, mineral-based flame retardants, nitrogen and or phosphorus-based flame retardants, and of course the intermescents. All of these can be additive flame retardants, and indeed they are probably the most predominant flame retardants available today. The additive flame retardants is a physical mixing of the additive or additive package with the polymer. The additive remains as a separate molecule. This leads to very flexible manufacturing approach to flame retardant addition. It's quite easy to add it at any step during the processes. It also then, by definition, lowers the cost of manufacturing compared to reactive flame retardants, which adds some extra cost, of course, to work that into the backbone. However, reactive flame retardants do have their advantages. When they form a chemical reaction with a polymer, it creates a new species. The reactive flame retardant is now permanently part of the polymer. It's not going to separate out. And the issue would be is that it has to be done, generally speaking, by the chemical manufacturer, because they have the equipment that is necessary to do that reaction on an industrial scale. The reactive flame retardants are resistant to blooming effects that you can see with additive flame retardants. That is, that in an uncured state, when it blooms during the curing process, these materials can come out or separate out of the polymer mixture, and they can form a layer then on the surface. Blooming is not a desirable effect, and you don't see it too much today, but it was at one time a particularly difficult problem. Additive flame retardants are simpler. They can be lower cost, not necessarily all the time. And the main advantage is that if you have a formulation, it's much faster to market if you have an additive flame retardant in there. The limitations are blooming. Processing can be difficult on the equipment. Some of these flame retardants can be corrosive, can be abrasive, and they can affect wear and tear on equipment. Also, the disadvantage to additive flame retardants is in some cases, depending on what you're using, you're going to have very high loading levels. It isn't as efficient as reactive flame retardants. The reactive flame retardants, generally speaking, it has better properties overall, better physical properties, thermal, mechanical, even electrical. They're typically easier to process because it's a simpler material than at that point. It's one material. And they have much higher temperature properties, generally speaking. When you have additive flame retardants, you're dependent upon the lowest performer. The other thing also is for manufacturers, they are a proprietary material, and so they can, have a business advantage that way. The difficulty with reactive flame retardants is that TSCA and reach can be an issue. If you're making a new molecule with a reactive flame retardant, you may have to TSCA list it and try and get it into reach, which is time consuming, expensive, and it doesn't happen overnight. There are going to be then fewer additives needed with it, and the cost of all of this, of course, can be an issue because it costs quite a bit to TSCA list or even to get something onto the reach list. So you're looking at a minimum of typically 6 months or 1 year, really, to get the at least the TSCA listing. Reach is, I think, even more difficult. Okay, the major places where flame retardants today get used is in furniture, anything from office furniture to household furnishings. Textiles, baby clothes used to have it. Some do and some don't, I believe, today. And it is best known also for industrial work clothing. Electronics are big on flame retardants. Printed circuit boards, cabling, enclosures of all kinds, they all have one type or another of flame retardancy. Electrical power generation, this is where you have your outdoor cables that bring power to your homes and to your factories from the power plant. Much of those transformers and other electrical devices, they are all flame retardant to a degree. The transportation area has a unique set of flame retardancy requirements. Aircraft is probably the one of the more difficult application areas, but there's also requirements for automotive, trains, buses, and so forth and so on. Building materials, as composites continue to make inroads into the construction industry, flame retardancy is something that is needed. So that is becoming much more of a growing area for them. In actuality, where they're using these things and how they're using them is as coatings, adhesives, and as composites for it in a lot of these applications. So, how do flame retardants work? People break them down into any number of mechanisms. Some of them overlap, but I've broken them down here into 3 of them. Your endothermic reactions, your barrier formations, and basically disruption. So if you think of the endothermic reactions, that's the heat side of the triangle. Barrier formation cuts off the oxygen. And you also have oxygen disruption or temperature lowering, where it works in the vapor phase. But endothermic reactions basically it raises the need for energy consumption to sustain the burn state. Barriers is just simply that. When a flame gets started, the decomposition immediately creates a flame-resistant barrier. And oxygen disruption, your halogens are here. They basically react in the vapor phase, okay? And it cuts off the oxygen, and it also interferes with the heat generation needed for the fire stability. It's because it absorbs the free radical ions, which propagate the fire. So, examples of the fire retardant mechanisms are things like magnesium hydroxide, aluminum trihydrate. All of these things basically do one thing: they break down. And the hydroxides and the trihydrates and those materials, they form basically what's water. And so they reduce the heat, and they basically put a damper on the flame spread. Barriers are intermescence. Basically, a char layer happens, and once this char layer forms, what happens is it cuts off the oxygen, cuts off the access to heat, and cuts off the fuel from the flame. And that's the way these things work. So ammonium phosphate are typically in many intermescent formulations. Phosphorus flame retardants on their own do the same type of mechanism. And melamine works through, which is a nitrogen-based flame retardant, works in this manner also. Your gaseous state is also brominated monomers, chlorinated monomers, and your nitrogen flame retardants. The melamines also will give off nitrogen, and that enters into the gaseous state, and so they work in two different ways. To some degree, brominated and chlorinated monomers, they also will form a char layer to some degree, and so they're very effective materials. Endothermic flame retardants break down when exposed to the heat, and the reactions, of course, draw off the energy needed to sustain the fire. Basically, it's a fire hose. It basically dampens water, and it enters into the gaseous phase, and that cools the fire state, and it can actually, with enough of the additive in there, actually stop the fire on its own. Gaseous state reactions, there's a lot of chemistry, but basically what you're seeing here is the components of the flame retardant break down, and basically in this case here you're seeing bromine. Bromine in turn reacts, forming HBr, and that process absorbs an awful lot of heat. The HBr also then reacts with other elements in the fire, and basically it starves the substrate or the fuel of oxygen needed to continue the burning state. I have here intermescent barrier formations, which is somewhat difficult for people to see. So what we're going to do is we're going to have a little demonstration with a video from one of the suppliers of intermescent coatings for, in this case, it's cardboard applications. But basically, you'll see here that the char layer cuts off the oxygen. It reduces the heat transfer to the fuel, And in effect, it basically knocks out two legs of the fire triangle. So let me see if we get this started. Okay. I'm going to put the video on now. And I don't see it running. Rick, what am I doing wrong here?
I think you just need to hit play on the video.
It shows that it's paused. Oh, hold it. Let me try again. Okay.
This demonstration features standard corrugated cardboard that has been coated with Flame Control 1010. Flame Control 1010 is a solvent-based intumescent coating designed to reduce the spread of flames when subjected to fire. Flame Control 1010 has been tested by UL in accordance with the ASTM E84 test specifications and has been assigned a Class A flame spread rating. 1010 dries to a flat finish and has the appearance of conventional paint. On contact with either a direct flame or excessive heat, 1010 intumesces or puffs up to form a dense protective foam layer that checks the spread of flames and retards heat penetration. As you can see, 1010 creates a layer of char that prevents the ignition of the cardboard substrate. As the char is removed, the cardboard substrate is revealed to be unaffected by exposure to direct flames. Turning the cardboard allows us to show the profile of the charred 1010 and exhibits the protective barrier that is formed. As we reverse the cardboard, the substrate is shown to be fully intact and unaffected by the flame. For contrast, when the uncoated cardboard is exposed to the open flame, ignition is almost immediate.
Roger, you have to take yourself off mute. Roger, not sure if you can hear me, but you need to take yourself off mute.
Do you hear me now?
Yes.
Okay. Okay. All right. So as you can see, the intumescent flame retardants can be very effective. You see the back side of the cardboard did not have any burn through. And so immediately when you apply the flame to the back side, it burns the rest of the way through. And that's the value of the intumescence. They create basically what's a foam char. Intumescent flame retardants are interesting because they actually themselves.
Roger, excuse me for just 1 minute. I'm sorry to interrupt you. You need to go back to the screen sharing and reshare your PowerPoint.
Okay. 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 Do you see it now, Rick?
Yes, thank you. And
Okay.
maybe while I have you paused, I could ask you one question that's been submitted. This might be a good time to do it.
Okay.
The question is, could you comment, please, on silica-based systems?
Silica-based systems are based basically on reducing flammability. They're really not known as flame retardants themselves. Basically, silica doesn't burn. And silica is used in a lot of formulations actually to reduce the coefficient of thermal expansion. The secondary benefit that they have is that since it doesn't burn, it reduces the amount of flammable material inside the formulation. So if you add 10% silica, say, to an epoxy formulation, it will reduce the coefficient of thermal expansion. It also reduces the amount of flame retardant that you have to add. And if you keep on adding more silica, the flammability decreases and the coefficient of thermal expansion also decreases. The problem is that eventually you'll add so much silica that you'll end up having a problem as far as having a workable formulation that can be processed. So there's really not many silica-based flame retardants. It's an inert filler material, and it can reduce flammability. Okay. With that, we'll go on to the next slide for intumescents. Basically, intumescents are formulations, and what they need is a catalyst for reacting the charring component. The catalyst actually kicks off the blowing agent, so you get an inert gas. Either CO2 is the most common. And what will end up happening is that as it foams up, it creates this foam char layer. It's a very popular and effective agent for coatings. And there's many different proprietary formulations for many different applications. There are some drawbacks to intumescents, but they are very effective. So you can see here on this slide, to the left is a proprietary phosphorus melamine-based basically charring agent that has been patented. But basically, you can see all of these catalyst sources. They basically trigger off the blowing agents, which are listed. Urea is very common, formaldehyde, and various other derivatives of many of these things. Charring agents can be anything from starch to melamine, phenol formaldehyde resins, and basically any other kind of polymers that can work in this application. So the next slide. Here we have basically reactive flame retardants, and these are very well known reactive flame retardants. In the electronics industry, you have both the tetrabrom bisphenol A on the lower right and tetrabrom bisphenol A epoxy right above it. They're very common in many applications. They've been commercially available for many, many years. In the center, you see melamine, and on the upper right is the melamine cyanurate. They are, in effect, also curing agents. So they're very effective to work into the backbone of the polymer, particularly epoxies. On the electronic side, the lower right-hand side, DOPO is one of the phosphorus flame retardant materials. It's been around for quite a while now, about 20 years, as a flame retardant. And it and its many variations are quite common for use in composites and electronics. So they basically incorporate phosphorus into the formulation, and the structure there also forms a very nice char. Additive flame retardants, there are a ton of them. There's the family of these metal hydrates, aluminum trihydrate, magnesium oxide are probably the two of the most commonly well known. And then there are a host of phosphorus materials. These are solids here. There are liquid types, but they are a oligomer of phosphate esters. Very often they're combined with nitrogen phosphate esters. You'll also find them with bromine and chlorine versions. They've fallen out of use because of environmental hazards and human exposure issues. So these are the additives for it. One thing also is there's still a lot of applications today that will utilize with the flame retardant the synergist. And synergists basically work with flame retardants to reduce the overall amount needed for the formulation to meet the requirements. Simply put, something like if you have 20% bromine in your formulation to get V0, by adding antimony, you could reduce that amount that's needed all the way down to 12%, 10% bromine. And there are reasons to use this. It makes the flame retardant more effective. And it basically, it also saves costs, and it may improve even the properties. The synergists typically work on one of the other flame retardant mechanisms. So antimony trioxide is one example, aluminum trihydrate is another. So if you combine bromine or you combine phosphorus with aluminum trihydrate, you get then a char, but you also then reduce the heat legs. So that's what makes them so effective, is the fact that they attack the fire in more than one way. Antimony trioxide, its use over the years has definitely declined. It still is used today. It is a suspected carcinogen. And so that has limited its use in new applications today. It's basically banned from use in printed circuit board applications, and the reason for that is that through the copper plating, antimony trioxide basically is a catalyst for the deposition of copper where you don't want it. And so what happens is they no longer use that for that application because of the problems associated with it. It's primarily used today as a synergist for flame retardants. There are some other small uses for it in catalysts and pigments, but it is still quite a few pounds of the materials are still sold today. We're going to now talk about flame retardant test methods. If you look on the internet, there are an awful lot of diverse test methods today for different industries and their applications. It's not unusual to have, for some applications, more than one test method that is being used, and that you have to meet those requirements. There are also a slew of organizations that regulate or oversee the test methods and their requirements, and many of them are industry specific. basically, when you test flammability, you're looking at the ease of ignition. How easy is the material to set ablaze? You want to know how fast the flame spread happens. You want to know how far the burn travels into the material. You are also interested, particularly in the transportation area, the toxicity of the smoke and the gases. The density of the smoke is measured. Heat measurements are also done because the fires will release heat energy, propagating the fire even more and even faster. And then there is some other methods, oxygen consumption. And in the case of like particularly thermoplastics, you're worried about the drip or the melt byproducts. As thermoplastic burns, what will happen is you'll form drips, and they can be flaming drips. And so usually they are, you're not going to stop the thermoplastic from melting, but you don't want that drip to set something else afire. This is the UL94 test method. I'm sure many of you are actually very familiar with it. It's a very easy test. It comes today. You buy a UL94 test method chamber. You simply, on the right here, it's simply a controlled flame that is regulated. And the test method describes on how to set up the flame. And basically what you're doing is you apply your sample or your specimen to it, and you're measuring the amount of time that the material burns, and it has to self-extinguish within a certain amount of time to pass the test for V0. It also has requirements for the spread of the flame, and this is done both in the vertical or in the horizontal position of the specimen. Depends again upon the industry and what the applications is. It's a very popular test that crosses many applications, and it's maybe only the beginning of the test methods that's used in some industries. Flame, smoke, and toxicity testing. This is basically aerospace, but this also relates to other areas like furniture, textiles, and so forth and so on. So you're looking at the flame ignition. That is, how long does it take for a specified flame to basically ignite the organic material. You're checking out the flame spread, and that's measured by how far into the sample the material is. Smoke density, it gets channeled, and basically through light measurements, the density of the smoke is looked at. The smoke's toxicity, how much carbon dioxide is there, how much nitrogen oxide, how much smut, let's call it. Is the smoke black or white? All of these things are tested, and the hazard of the smoke that is released is evaluated. Heat release rates. This all relates to the way that the material burns. As it burns, is it giving off enough heat to continue the flame? You don't want it to, so you're looking at very low heat release rates. The total amount of heat release that is done when a sample is burned through. And this is all described as in the FAR 25.853 test. It's an aerospace standard. It actually all of this comprises multiple tests and multiple equipment. And all of this is done for things like aircraft interiors, transportation of buses, public transportation. It also is even related to things like subways and stuff like that. There's also a military version of this for aircraft. Limiting oxygen index. You'll see this around, but I think over the years there's been less and less with it. It basically is a device that measures the minimum amount of oxygen that is needed to support a burning specimen. So on this particular unit, you'll see here the tube, a specimen is mounted in it, and it is then fed a certain amount of oxygen, and the minimum amount is then determined as a percentage. And basically, the limited oxygen index values that are greater than atmospheric oxygen is considered actually a flame retardant. So it needs basically a lot more oxygen than the atmosphere is providing. And so it can be then a flame retardant or a flame retardant material. It's not widely used as a test standard, since this is doesn't account for many other factors that are necessary for it, but it is a way of finding out if something is flame retardant or not. Those are the most common tests, but there are actually many, many other tests. All of them involve different burning scenarios. They will build houses, chambers, all kinds of things for testing. All of that is then covered by regulating bodies and trade organizations from different industries. And there are a lot of them, and it's not unusual to have more than one regulating body and more than one trade organization actually involved in the let me get rid of this, involved in the particular applications. On top of which you also have consumer groups, which are particularly active in areas of furniture, textiles, and basically chemical manufacturing. Environmental organizations also have had a large impact on flame retardant business. And even global organizations have impacted electronics and other applications. Global organizations have been important because they have been setting the marketing trends and actually have forced US manufacturers to comply with requirements in Asia and in Europe. The first primary governing body you have to be concerned with is the US government. They have basically guidelines for safety testing, the use of flame retardant chemicals, and the requirements for different types of applications. Some of the agencies inside the government that are involved in all of this is the Environmental Protection Agency. They basically look at the chemicals that are used. They will identify them and classify them as far as toxicity, persistence in the environment, quite a few things. Department of Transportation, obviously they're looking at flammability of the public that are using buses, trains, etc., etc. The FAA, very obvious. Planes can catch on fire, and when accidents happen, they become quite an investigation. The Consumer Product Safety Commission has been involved over the years. Many years ago, there were issues with children's clothes in general, because they were allowing people to be exposed to very hazardous chemicals. And then, of course, the Department of Defense has its own set of regulations and guidelines. One of the best groups that is known is Underwriters Laboratory. It's a very well-known industry and trade group. It primarily covered the electronics area, but also it also oversees many other industrial applications today. The UL94 test is that test from Underwriters Laboratories. It's one of the best and most broadly used test methods today. It's a simple test to perform. You can build your own chamber with the necessary requirements in-house. You don't even have to go out and buy it. You simply measure the flame spread, time to extinguish, and any generation of flame drips. So it's good for both thermosets and thermoplastics. It certifies products that meet the appropriate flammability requirements. And so when you have a UL certification, it means that you have a product that meets the flammability requirements. And you pay for that through that. And that was particularly important in the 50s and 60s when voltages were much higher with electronics and there was a greater risk of flammability. ASTM is another area. We all know it for many of the test methods. They are duplicated from specific industry test methods. Usually if you have the UL94 test does have an ASTM equivalent for it. It reads exactly the same the last time I looked at it. And in many industries, the ASTM test method had become the specific identifying test method for that application or industry. So it's I think at one point there were more than 60 different test methods in ASTM. There may be much more today. Some of the other notable organizations to be aware of, PINFA is a trade organization for non-halogen materials. So basically it's phosphorus, inorganic, flame retardant materials here in North America. The Green Science Policy Institute is a organization primarily for consumer advocates. They're very active as far as textiles and furniture goes. They advocate basically furniture. They question the use of flame retardants in those applications. The American Chemical Society is involved in trade issues in the science. There's a bromine council for manufacturers. Chlorine almost has dropped off the map, but there are many, many more organizations, and you have to look at them for your particular area. Flame retardants have health concerns. So over the years, many flame retardants have been banned because of exposure concerns to humans. They're either carcinogens, they can be materials that impact fetal development, and so there's many concerns over them. Also, the end of life concerns with these things have been a big problem because we incinerate everything. And so we're releasing these things into the atmosphere at one time. Many brominated and chlorinated compounds have been proven to be carcinogenic. Issues in many years ago showed up in textiles and furniture. And there is still occasionally some concerns about this even today. The brominated flame retardant class is one of the primary ones that has been a problem is the bromodiphenyl ethers. Decabromo, octabromo, all of these were at one time very common flame retardants, and it was once the largest class of flame retardants around ever. They're additive materials, they're solids, and in and of themselves, they're usually not a problem. The biggest difficulty with these things is the hazardous decomposition products and the fact that they are persistent in the environment. theoretically, they've been banned in Europe, but there are still places and applications that use brominated flame retardants and have been given, special leave to do it. But there is a widespread movement away from this. But brominated flame retardants are still used today, and they have this as the major problem. When you have electronics with tetrabrom bisphenol A or decabromo or any other materials that are flame retardant with them, they take them and they recycle them, and they will basically burn them in incineration. And incineration causes these two decomposition products, both of which are toxic. So what you're seeing is dioxin and furanes that are formed, both in the brominated version and in the halogenated version. Bromine and chlorine, I'm sorry, versions. These are very common decomposition products from the waste disposal incineration. Some studies over the years have shown that it is basically a problem with low temperature incinerations. This is around 550 degrees centigrade to 650 degrees centigrade. Both of them are carcinogens. They've also been studied and understood to cause severe developmental problems in infants. And in everyone else, it basically can damage the immune systems. Bromine has not been as toxic as chlorine. Chlorinated dioxin and chlorinated furanes are very toxic, but bromine and chlorine, as a result, are today regulated in this. These do not form when you drive up the incineration temperatures to about 700 degrees centigrade, something greater than 650. So the amount is either reduced or doesn't even show up. But that's why both Asia and Europe basically started the non-halogen movement, because they were their incinerators operated at lower temperatures, and so they were releasing these things into the environment. The US runs at higher temperatures. Okay, there's more than 2 million tons of flame retardants that are sold in the world. The leading applications are construction, electronics, transportation, just on a volume basis. The furniture and textiles area have a smaller and possibly declining applications. I found it interesting, but Wayfair, if you go online, you can find furniture that is with bromine and their equivalent without bromine. So your couch or your table that you want can be flame retardant, or it can be not flame retardant, your choice. And they're not the only ones. The biggest area that is growing is the non-halogen flame retardants. So some old flame retardants are making a comeback, and new ones are making gains against the brominated and chlorinated flame retardants in the past. Safety is a concern with all of the flame retardants. Disposal and degradation are major issues. Their persistence in the environment should be added also here as a major concern. Human exposure to flame retardants from furniture and textiles, even today, as late as 2020, are still a concern from consumer groups that are advocating their elimination, particularly putting forward initiatives in California. So California is probably ahead of everybody else as far as regulating these materials. So as I said, the development has shifted to basically to non-halogen flame retardants today. There is much more interest in mineral flame retardants. They're not as effective, but they are safer, cheaper, and they're finding ways to work with them. As much as they have some drawbacks, they people are re-looking at them. They're looking at things even like silica. This is where the silica came in too. There is interest in reactive flame retardants without the bromine or chlorine. Things like DOPO have come on in the last 20 years. There's also some patents on boron flame retardants. I know because I have one. Nitrogens, melamine's been around for quite a while, and other nitrogen flame retardants have been patented. Even sulfur as a flame retardant, contrary to popular belief, is being seen as a possible flame retardant material. The other unintended consequence of all of this is that the use of polyimides, benzoxazines, and/or phenolics as alternative to epoxies have been pursued. In electronics, benzoxazines have found a niche in non-halogen applications simply because they are materials that do not burn as much as the epoxies do. Whether it's an epoxy, a polyester, or even a polyurethane, benzoxazines basically do not burn as much as them. So you either don't have to flame retard them, or you're adding a lot less of the flame retardant in them, which basically improves performance, and it can also reduce the cost. So benzoxazines, phenolics, and polyimides are finding new life as materials that inherently burn less. You get halogen-free items, furniture and textiles that are basically non-flame retardant. And they do have a place today because, unlike years ago, people do not fall asleep in the chair with a lit cigarette and an ashtray. So there is less and less a need for some of these things, and some people are actually allergic and or have had adverse reactions with furniture that has halogens, and there have been some documented cases of that. So, all in all, the key takeaways for all of this is that environmental and health concerns dominate in pretty much all markets where flame retardants are used. Today, the trend in question is, do you even need the use of flame retardants at all? So whether it is furniture or whether it is your cell phone today that you actually carry is most likely to be a non-halogen based material. But electronics today are using less and less voltage, fewer amps. And so with such low power that they have, the question is, do you even really need a flame retardant at all? They haven't changed the requirements yet, but it is being discussed in various industries. California, as far as regulation, is leading the way to banning flame retardant chemicals or limiting their use. And R&D today focuses pretty much exclusively on non-halogenated materials, primarily phosphorus. And these phosphorus and other non-halogen flame retardants have grown in many, many applications. One thing to note, even in electronics today, 60% of the infrastructure electronics, I'll call them, still use brominated flame retardants because of their superior performance otherwise. In consumer electronics, that is where halogen-free materials have come to the front. Nobody really wants to sell something that a cell phone that is not flame retardant to begin with, even though the risk of it is very low. but also today, conversely, Samsung some time ago had cell phones that their lithium-ion batteries basically exploded and burned. And the argument is that they didn't, that the situation wasn't worse because the rest of the electronics was flame retarded, and so the damage wasn't as severe, but it is a concern. So it's a very confusing time as far as flame retardants go. And at this point, this is the last slide of my presentation. So I'll open it up to any questions that anybody has.
Thank you, Roger. We haven't had any additional questions submitted, but we'll give everyone a moment to submit any questions they may have.
Okay.
And thank you, Roger, for an excellent presentation. While folks are considering whether to submit questions, please mark your calendars for our next webinar, November 18th, with Jeff Gautreaux presenting on curing and gelation. Roger, no other questions have been submitted.
Okay.
Thank you very much for an excellent presentation. You did such a good job. Nobody has any questions.
It's a very large area. There might be questions and later on, and my contact information is here. Please feel free to write me an email or even call me if you have some specific questions.
Thank you very much. Have a great day, everyone.
Bye-bye.